Hi, my name is Noson Yanofsky. We're doing the homeworks for section 3.2, and as always you should try to do the homeworks on your own. Now this homework is particularly not simple and you might have trouble, but at least you should spend some time thinking about what it means and trying to do it on your own. Okay, so the problems are in chapter 3, number 18, 19, 20, 22. Okay, and we're going to do that. So number 18, a Turing with a double infinity tape. Okay, show that this type of Turing machine recognizes the class of Turing recognizable languages. So let's just do number 18. The usual definition of a Turing machine has a tape, and the tape is infinitely long, one way. Okay, the book now asks, what happens if you have a Turing machine with two-way infinite? Okay, and it starts looking here, and it can move to the left, it can move to the right, it can move to the left, it can move wherever it wants. Okay, now this is a little less restrictive because here you can't move to the left. You can always move to the right, but you can't move to the left. So this is less restrictive, and you can have memory over here, you can put your input over here, etc., etc. Okay, now you might think, hey, this is much better than this. So let's write that out. So this is a one-way infinite Turing machine, and this is a two-way infinite Turing machine. Okay. It turns out, and so you might say, hey, this is much better than this, and I clearly want this type of machine rather than that old-fashioned this machine. But it turns out as follows. A one-way infinite Turing machine is equivalent to a two-way infinite Turing machine. Okay? And the proof is as follows. Okay? Now, let's do it one. Such a machine can clearly be mimicked by such a machine. In other words, you're going to have, what you do is you just put a symbol X here, and you copy whatever's here, you copy there. Okay? And if a machine can do anything with this input, you just have this input, and you just never go past the X. If you see an X, that means back up and go to the right. Okay, so whenever you see this new symbol called X, that's going to be your barrier. You can't go further, and you can do whatever he does, he can do also. Okay? The hard part is the other way, right? Show that such a machine can be mimicked by such a machine, a one-way infinite tape. Okay? And the way it's done is as follows. Okay? Let's assume you have a big tape, and it has on it A, B, A, X, B, Y, Z, D, P, Q, R, S, T, etc., etc. Okay? And there's blanks over here, and there's blanks over here. What you do is you make this two-way infinite tape, think of it as a one-way infinite tape. And the way you do that is you somehow, forget about what it's looking at, somehow chop the tape in half. Okay? And chop it in half and bend it this way. Bend this part around like this. Okay? And then we're going to make, from that, we're going to make a one-way infinite tape. But this one-way infinite tape has two tracks. So this is a multi-track Turing machine. Now, different than a multi-tape. A multi-tape Turing machine is you have two different tapes and the eyes are pointing in two different places. Here you have one tape, but you're going to have two tracks on the tape. Okay? And whereas this has little squares all along, this also has little squares, but here's the main but. This tape can deal, at each square can have two symbols. not one symbol. Here, every tape, every dot, every space has one symbol. Here we can have two symbols. Okay, and so here's the symbols: P, Q, R, S, T, blank, 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 dot, dot, dot. Okay, that's the symbols on the top track. What about the symbols on the bottom track? Well, like I said, think of this as bending this around and letting the infinite part here go around here. But I'm going to write the symbols the right way. I'm not going to have the symbols upside down. So this is going to be a D, Z, Y, B, X, A, blank, 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 dot, dot, dot. Okay, now, how should this two-track Turing machine, how should this Turing machine be mimicked by this Turing machine? Well, if it's over here, if the tape is over here, so fine, then the tape is over here. Ignore what's on the bottom symbol, okay, and do exactly the rules that he says. So if he says change the S into the letter 9 and move to the right, so you change the letter S into the letter 9 and you move to the right. Okay? And if he says change the letter T to the letter U and move to the right, move to the left, so you change the letter U and you move to the right. Okay? And you change the letter U and you move to the right. Or the left, whatever. Okay? So on this part of the tape, it's no problem. Okay? Just ignore the bottom symbols and do that. Okay. But if you're on this part of the tape, then what do? Okay? So here you're pointing to the Y, and the main difference is that here you do whatever this tape should do, whatever this tape does, just looking at the bottom symbol. Okay? But if he moves to the right, then he should move to the left. Okay? So if you're going from Y to Z, then you should go from Y to Z, because you turned the tape upside down. So you have to do that. Okay? So he mimics him on this side of the tape by doing the same rules that he does, except afterwards, if he moves to the right, he moves to the left. If he moves to the left, he moves to the right. Okay? A very cute thing. Obviously, you have to worry a lot about what happens if you're here. So let's think about it. If you're pointing to the P and you move to the left, then you stay there. Or this is a one-way tape, so you might as well just move to the left, and which will stay there, and then you start dealing with the bottom things. Okay? The interesting thing is, whereas here the tape alphabet was gamma, here the tape alphabet has two symbols. So the new tape alphabet, gamma prime, is going to equal to gamma cross gamma, because it could, every time it has one of two symbols. Great. That's the end of 18. Okay, let's do 19. A Turing machine with left reset. Okay, let me just tell you what that's about. So, the regular Turing machine is as follows. This is 19. It says, tell me what state you're looking at, tell me what symbol you're looking at, I'll tell you where to go, and I'll tell you what to write, and I'll also tell you left or right, to move to the left or to the right. Okay, now we're going to change this. We're going to allow to go to the right, but also to go to something called reset. Let me tell you what reset is. If you're here, you can go to the right. That's simple. But you can also go all the way back to the beginning. You can't go to the left. Go all the way back to the beginning. Okay. To me, the first time you see this, you say, wow, that's terrible. That's very weak compared to this, where you can go to the left and the right. But this seems very weak because you can't go to the left. Now, okay, turns out these two types of Turing machines, this is called a regular Turing machine, and this is called, oops, and this is called a left reset Turing machine. Turns out they're equivalent. Okay, and so I'd like to show you how they're equivalent. One way is not hard, the other way is hard. Okay, great. So the other way is hard. And I don't expect you would get this. If you didn't see it before, it's actually pretty painful. Okay, so let's go through it and let's see how to do it. Okay, first of all, we have to show that this guy can mimic this guy. And that's not hard. Okay? Obviously, if he's going to move to the right, he can move to the right. No problem. But if he's going to move to the right, he will also move to the right. So, in other words, if you have a Turing machine that does this, then you can write another Turing machine of this type that does this. Okay? Okay. The hard part is, or the semi-hard part is, what happens if he has a reset? Okay? And the way you do that is very simple. Every time he has a reset, what you do is you go into a subroutine. You go into a subroutine that basically says, okay, go all the way till the beginning. Go back till the beginning. Now, I don't know if there's an extra symbol here to show what the beginning is, but just keep on, rewind past everything till the beginning and then stop. Okay? So, this machine can mimic reset. Very nice. That's the easy part. The hard part is showing that this machine can mimic this machine. Okay? So, one way is pretty simple. Ready? If he goes to the right, he should also do the right. No problem. Okay? Now comes the hard part. No, sorry, let's okay, if he's pointing here, okay, and let's imagine on the tape is the letters A, B, X, Y, T, Z, F, G, R, no, not R, S, X, blank, 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 blank. Okay, so if this machine, now this is a reset machine, we have a reset machine, and we want this regular machine to mimic the reset machine. So if he moves to the right, do whatever you want and move to the right. So he will also move to the right because he can move to the right. Very nice. Sorry, I'm talking about, we want this machine to mimic this machine. Okay, so if this machine moves to the right, he can also move to the right, no problem. Okay, what's the hard problem? Okay, the hard problem is if this machine moves to the left, how am I going to make this machine to mimic it? Okay, how is a reset machine to move to the left? Okay, let me give you a first answer, and the first answer will be wrong, and then we'll fix it and we'll get a better answer. First answer is as follows. Whenever you have in this machine, you see move to the left, instead of moving to the left, put on top of this symbol, put a hat on that symbol. Okay? And then go into another state that goes automatically resets. Okay? Great. Now, I want to move to the left. I want to move to the F. Okay? So, here's the thing. Move till you get to the hat. The thing before you get to the hat is the F. The thing You made a symbol where you were. You want to get this way. So now slowly move forward until you see the hat, or until you see the element before the hat. Okay, now I see an F. I don't know what the next element is. I see a G now. I see a G hat. I went too far. Okay, I really wanted to work with this. In other words, let's go through this again. This Turing machine made a left. I want to mimic this Turing machine with this Turing machine, which only has a right and a reset. So how do I do it? I change this, and then I reset, and I start looking for the hat. But the minute I find the hat, that means I went too far, and I can't do that. Okay, so that doesn't work. Okay, so we need a better way of doing it. Okay, and the better way of doing it is, instead of going towards the left move the entire string to the right. It's a funny thing. Instead of going to the position to the left of the hat, move the entire string over. Okay? Move the entire string to the right, and then you'll see it. So let's do this. Okay? It's a funny thing to do, and again, it's not trivial, but let's do it. Okay? So I see an A here. Great. I'm going to keep in mind, in other words, I have to have more states. I'm going to keep in mind that there's an A here, and I'm going to make a blank out of it. Okay? You know what? I don't want to do that. Shoot. Okay. I'm going to cross the A out and make a blank. Now I'm going to go next, because I can move right. Okay, I'm going to keep in mind I just saw an A. I'm going to cross out the B, put down the A. But I'm going to remember that I saw a B. I'm going to go into a state that says, this is my move string state. I'm going to say, oh, I'm going to move string state. I just saw a B. I crossed the B out. I put an A. Fine. Now I'm going to move to the right. Boom. Okay. I cross out the X. Keep in mind that I saw an X, and I put the B down. Okay. Notice what I'm doing. At every point, I come here. I put down what I saw before. I saw before an X. Okay. I keep in mind what I just crossed out. Come here. I put down an X, Y, and I keep in mind the T. I put down the T, and I keep in mind the Z. I put down the Z, and I keep in mind the F. Fine. I finally come to a hatted letter. Okay, a letter with a symbol. And I continue, but I keep the hat there. So I cross out G hat, and I put in F hat. No, let's cross out G hat, and I put in F hat. Okay, and I keep on doing this. I just crossed out a G, so I make this G. I just crossed out an S, so I make this S. I just crossed out an X, so I make this X. Now I have the same string, but I have it moved over. The string was ABXYT. The string is ABXYT. It goes on. Okay. Now I come to a blank. I don't have to move a blank anymore. And so when I just finished doing this, I reset again. Okay. Now search for the hat. Search for the hat. I found the hat. Okay. And guess what? The hat, F is under the hat. Now I deal with that. Okay? So every time there's a reset here, I go into this special subroutine. And the subroutine puts a hat on the letter you're looking at, backs, resets, and then step by step moves the whole stupid string over Except the hat. Leave the hat where it is. You can leave your hat on. Great song. Don't watch the video. No, you can leave your hat on by Joe Cocker. And you can and then you I'm sorry, got confused with Joe Cocker. Put a hat on, reset, slowly move forward, bringing the whole string forward, reset, slowly move forward till you find the hat, and then you work with that. Okay, so that's the way you mimic a left with a right and a reset. Pain in the neck. Okay, good. Next. Okay, let's do number 20. Okay, number 20. I'm going to read number 20 because it's a little bit confusing. A Turing machine with a stay put instead of a left is similar to an ordinary Turing machine, but the transition function, so this is an ordinary Turing machine, the transition function now is either move to the right or stay. Now in class we did a left, right, and extra stay. This doesn't have a right, it just has a right and a stay. At each point the machine can move its head right or let it stay in the same position. Show that this Turing machine variant is not equivalent to the usual version. What class of languages does these machines recognize? Okay, so you're going to have a bunch of letters. You have a bunch of letters here, and at any point you can move to the right, or you can just stay there. Now you can also write things here. Right, what you want, right, what you want, etc., etc. You can change, but notice what you're doing. You're either going ahead or staying. Okay, you're either going. Whereas the Turing machine goes like this, or like this, or like this, or like this. Here you can go ahead or stay. Okay. Now I'm not sure. Oh, okay. If I can only go this way, then I definitely can't mimic a left move. So they're not equivalent. Such Turing machines and such Turing machines are not equivalent. Okay, but then it finishes off and says, what class of languages do these machines recognize? Okay, now I think such a machine can stay in an infinite loop. Okay, it's like when you play chess. You know, you can go back and forth and back and forth. Well, you can just stay in a machine that just stays. However, when it does give an answer, think about it. All you're doing is moving ahead. Well, we had another machine that just moves ahead. Okay, and what was that? And that was finite automatons. Finite automatons just move ahead. So I think they recognize the same language as finite automatons. I could be wrong on this one. And I'm sure someone's going to find an error and tell me I'm wrong and put it in the computer. And I'll write the comments. Okay, great. Okay. The next problem, 22, is something that students always ask about. Whenever I teach them that a to the n, b to the n, c to the n is not context-free, they say, well, you can't make a push-down automaton for this. Let's see why not. Okay, you push down all the a's, and then for every b you pop one. That's good. Okay, but then since you popped it, you come to c's and you don't know how many c's you have. That's a problem. That's a problem. Okay, so you've lost how many c's you have. That's a problem. So you can't do it. And always, always, always a student says to me, hey, what happens if you have not one stack, but you have two stacks? Okay, so then watch what you do. You push down the a's. Okay, so you have A. Then every time you see a B, you do two things. You pop off, and also you put onto the second stack the B's. Then, when you see a C, you pop off the the B's here, and then you can do it. And that's true. Okay. The problem was push-down automatons had only one stack, by definition, and you're making up a new thing called two stacks. Okay, so the book talks about that. Let k PDA be a push-down automaton that has k stacks. Thus, a 0 PDA is a PDA without any stacks whatsoever, is an NFA, and they recognize only regular grammars. And a 1 PDA is a PDA. You already know that a 1 PDA are more powerful than a 0 PDA. Show that a 2 PDA are more powerful than a 1 PDA. Okay. Okay, and the way I want to do it, the way I want to show it, is we're going to look at a 2 PDA, and guess what? It's equivalent to Turing machine. If you have two stacks, it's an equivalent to Turing machine. Let me show you why. A, B, C, D, E, F, G. Okay, you have a lot of symbols on your infinite tape. This is an infinite tape, but eventually you get blanks. Okay, you have a lot of symbols, but you knew it. Okay, great. You're pointing here. I want to mimic this. Stop. Stop. Okay. First of all, why is a Turing machine? How can a Turing machine mimic a 2 PTA? Well, this computer over here, or your computer, you can mimic a stack. You can mimic a stack. You learned how to do that in the beginning of the first class of data structures. Okay? And you know what? In your computer, in your Java program, in your Python program, you can mimic 2 stacks. Okay? Well, a Turing machine can do it also. Well, the way it does it is, it just goes to the end of the input, and it has a memory place there. Okay, and then it goes further on to the memory, further on, and it has another memory place. And you mimic both of these stacks on your Turing machine tape. The hard part is the other way. How do I mimic a Turing machine with a double stack? And the answer is as follows. I put A, B, C, okay, D, okay, E, stupid, G, F, E, okay, and the way I do this is as follows. This is on my tape. This is on my tape. Let's say I don't want to change anything on my tape. Well, I can change it. Let's say I'm here and I want to change it to a D prime. Here's what I do. Okay, I change it to a D prime. So change the D to a D prime. That's what the Turing machine does. Here's what I want to do. I'm going to pop off the D, change it to a D prime, and then put it back over here. Now, question, do I move to the right or do I move to the left? Okay, if I move to the right, then here's what you do. Pop off the E from the second stack, pop it, put it on here, and we're dealing with that. Okay, we're always dealing with what's on top of this stack. Okay, and again, what are you going to change the E to? Change the E to an X, I don't care what you do, etc., etc. Okay, great. If I again move to the right, then again I pop what's here and I push it on there, and then I deal with that. So you're always dealing with what's over here. Now, in contrast, okay, so we'll change this F to an F prime. In contrast, let's say you change this to an X and you change this to an F prime, and you're pointing here. In contrast, let's say I'm moving this way. I'm moving to the left. Then what I do is pop it off here and push that here, and when you pop, you're going to come now to the X. It was an E and now it's an X. Okay, and you pop, and if you want to go further, you pop it off. You're going to always you're always dealing with what's here. So every time you move this way, you move it like this. Okay. The idea is as follows. You have an infinite tape. Very nice. You have two stacks that are each infinite. but you can break the stack into two, break the tape into two, and then like what's that kid's what was that kid's toy? I can't remember. Okay, go up and down like that. Okay, I'll remember the name of the toy and I'll put it in the comments. Okay, so we can go up and down like that. The point is, you have random access memory here. You can go to any place on the tape. You're not going to lose information when you pop off the first stack because you're going to put it on the second stack. Okay, and so you have total information and whatever can be done there. Okay, great. What about 3PDA? Well, 3BTA is also equivalent to Turing machines, and all of them. Basically, the reason is as follows, is because Turing machines are the most powerful thing in the world. Okay, and a Turing machine can mimic a 3PTA because a Turing machine can mimic because just like your Python program can mimic you can write a Python program that uses 3 stacks, so too a Turing machine, and also 3PDA can definitely mimic a Turing machine because you can just do it with 2 of them. I showed you how to do it with 2 of them. You don't even need a 3. So they're all equivalent. Doesn't matter how many stacks you have, they're all equivalent to Turing machines. Turing machines are the most powerful things. Okay, that takes care of that. Those are 4 different variations of Turing machines, and lo and behold, 3 of them are exactly the same and 1 isn't.